Okay, so this is the third and final talk on critical phenomena. My Sumit will start with it.
Oh, okay. I'm sorry for I had to reschedule this. The timing of this talk. It was sort of unavoidable. Thank you very much for accommodating my request. So today, I will put all we have learned over the past 2 lectures to try to understand some aspects of quantum quench when it comes across a critical point. So as we discussed yesterday, a critical point is characterized by long-range correlations. This means that the correlation length diverges. Now, for a thermal transition, we need to adjust the temperature. To arrive at a critical point. For quantum criticality, this can happen even at 0 temperature, but there is some other coupling or some other parameter in the Hamiltonian which needs to be tuned. It is conventional to write the Hamiltonian near the critical point in the following way. Let me put it outside. O of x is an operator, and sorry, OI of x is an operator, and GI is a parameter. H critical is the Hamiltonian of the critical theory. What characterizes this Hamiltonian? So for H critical, for GI equal to 0, the energy gap vanishes. What does this mean? This means that if I take the Hamiltonian H critical and write the spectrum, there is a ground state. Let me call it the ground state 0. And for GI not equal to 0, there is a gap. What this means is that all the excited states sort of start like this. When GI equal to 0, this gap in the spectrum, which is denoted by EG, goes to 0. So this is the main characteristic of a quantum critical point, and this will play the most important role in our discussions. It also turns out that when the energy gap vanishes, at the same time, the correlation length also goes to infinity. Now, we saw that in our discussion of thermal transitions, that the correlation length near the critical point goes as some power of T minus Tc, where nu is called the correlation length exponent. In the same way, for quantum critical points, we have exactly a similar relationship where the correlation length goes as some parameter. This is a parameter in the Hamiltonian raised to the nu. And in our example, we can of course redefine the parameter, the zero of the parameter. So for a Hamiltonian, which is of the form that H critical plus sum over many operators, sum this. So for example, we can take a relevant operator, G, so let me call it G, which we have taken to be lambda minus lambda C, because at G equal to 0, the theory is critical, namely there is no mass gap. Okay. Just as the correlation length, so we will write this goes as I've just taken one of those couplings, G raised to the power minus nu. Now, just as the correlation length behaves as diverges as a power law in the departure from the critical point, the energy gap should vanish as a power of the critical point. So it should go as G raised to the some power. What would be this power? We call this power Z times nu, where Z is called a dynamical critical exponent. And let me explain what does this actually mean. So let's do some dimensional analysis. We will assign a dimension to every quantity, just as you do in any physical problem, where the dimension of length is taken to be -1. Okay. So this means, and I'm going to use units where h bar and c is equal to 1. So this means that the dimension of momentum, for example, is going to be +1. If this is a relativistic theory, the energy momentum dispersion relation is like this. So then the dimension of energy will also be +1. In a non-relativistic theory, you could have something like E goes as k squared, just in ordinary non-relativistic theory. Kinetic energy goes as the momentum square. Or in general, you could have these kinds of theories are called Lifshitz theories with non-trivial values of Z. So Z equal to 1. Sorry. No. This is the relationship. So z equal to 1 for relativistic. So z equal to 2 for ordinary non-relativistic. Non-relativistic free theories. So in general, for a many body system, z can attain non-trivial values. We will not be concerned in learning how does that happen, but using the fact that at the critical point or near the critical point, and this is something I emphasized yesterday, things can be obtained by dimensional analysis. And why that is so? Because near ordinary critical points, for ordinary critical points, the correlation length is the only scale that matters. Since, because of this relation, and because the fact that the momentum has dimension +1, what this means is that near a quantum critical point, we must have the energy gap going as the correlation length raised to the minus z. So this is simple dimensional counting. Okay, any questions so far? Because this is in fact the main, one of the main points which you would like to emphasize. Good. So equipped with this knowledge, so basically, so this tells you that if xi goes as g to the nu, so g to the minus nu, the energy gap goes as g to the power z nu. The correlation length diverges, the gap in the spectrum goes to 0. This is what characterizes a critical point. Let's now come back to the question of quantum quench. In a quantum quench, there is some parameter in the Hamiltonian, and let us take this parameter to be g. So what happens is that this parameter has a time dependence. It starts with some value g0 at t equal to minus infinity, and it has some other value g1 at t equal to plus infinity. And using the simple exercise of having a very sudden quench, namely a sudden change of this coupling, the lesson, the physical lesson we learned is that if I prepare the state at early times, for example, in its ground state, at late times, the system gets terribly excited. A critical quench happens when at some time, at some intermediate time, the Hamiltonian, the instantaneous Hamiltonian, and I'll explain what does that mean, is critical, that is, the mass gap or the energy gap vanishes. In our example, for example, you could have a situation where the flow of the coupling is, something like that. This is at t equal to 0, G becomes 0. And from our definition of how we define the G's, go back to this fundamental equation. Here I've written as a sum over many different operators. But if I just take one operator, which is the relevant operator, G equal to 0 means the Hamiltonian is critical. As we will see, something very interesting happens when the quench is of this type. To understand this, we need to understand the notion of what we call an instantaneous spectrum. So let's go back to the basics of quantum mechanics. We have a Hamiltonian, which in our case is a function of time. And we need to solve the Schrodinger equation. How do we usually solve the Schrodinger equation? Just to remind you, when the Hamiltonian is in fact a constant, it's not a function of time, we solve this equation in 2 steps. The first step is a mathematical problem, nothing to do with the physics, which is to find eigenstates of this Hamiltonian. Sometimes this equation, which is the eigenvalue equation for the Hamiltonian, is called the time-independent Schrodinger equation. But I would like to emphasize, this is not really a physical equation. This is simply a mathematical problem, a trick which we use in order to solve the main equation, which is the Schrodinger equation. What we then do, staying with a constant Hamiltonian, is we expand the state into some coefficients which are time dependent and the eigenstates of this Hamiltonian H. We plug this into the Schrodinger equation, and this equation then becomes very easy. For each E, each N, we get an equation which looks like this. And that can, of course, be very easily solved. Once we solve that, we have a solution of the problem. This is the way we solve all problems in quantum mechanics with a time-independent Hamiltonian. We can try to do the same thing when the Hamiltonian is a function of time. The analog of this problem, of this mathematical problem of finding eigenstates of the Hamiltonian, will look something like this. In this equation, t is simply a parameter. For example, if I have a Hamiltonian, which is like a harmonic oscillator with a time-dependent frequency, and this is the example which I had used. If I want to ask what is the ground state, what is the state 0 of t, which is, this has a wave function. Which goes as e to the minus I omega of t x squared. So basically, what we are going to do is you take this Hamiltonian, treat t as just a parameter, and solve the eigenvalue problem. As I emphasized, this is a mathematical problem, so I can always find a solution of this. The next step, which we did in our discussion of a time-independent Hamiltonian, is to substitute, is to expand the states in terms of these. You can continue to do the same thing. And you can substitute this into the Schrodinger equation. But now you start seeing that the problem becomes complicated. The problem becomes complicated because there is a t everywhere here. The eigenstates depend on t. The eigenvalues depend on t. For this reason, these are called instantaneous eigenvalues or instantaneous energy levels. It is as if you take the Hamiltonian at some time t, take that Hamiltonian, calculate its energy spectrum. Those are the eigen energy spectrum, instantaneous energy spectrum at time t. Go to another time, you get a different spectrum. Because t is hanging out everywhere, things become very complicated, and the equation for this A tilde is rather complicated. So this may or may not be a very useful way to proceed in trying to solve the problem. But there's nothing wrong in doing this, so let's do this. For reasons which will take a little while to explain, it is useful to define a new function which is given by this. This is just for simplicity. However, in terms of this new function, it is not very hard to show that the equation satisfied I'll write for a k of t it looks a bit complicated, but we're not going to use this very much. I don't have much space here. This object looks a little bit abstract, but in terms of wave functions, this object is nothing but something like this. I'm not going to use any of the details of this equation. The important thing is that this object can be rewritten in the following way. when k is not equal to n, then you get a result and is given by what is del H del T? For example, in the harmonic oscillator, del H del T is omega dot times x squared. So far, everything is exact. It can be also shown that by a choice of phase, you can choose the diagonal part to 0. Now, suppose I prepare the system in some eigenstate of h at t0. T0 is the initial time, which I call n. Then the result of this is that dan dt in fact can be chosen to be 0, and dak dt for k not equal to n has a complicated expression on the right hand side, but it involves a matrix element which looks like this. So now you start seeing this kind of doing things is useful. What this tells you that if at early times, so there is the initial Hamiltonian at some time t equal to t0, the Hamiltonian is like this as a function of time, and then it starts changing as a function of time at some point. So this is t equal to t0. And if the state of the system is n at that time t equal to t0, then this equation says that the component of the wave function which is in the n direction does not change in time. The component of the wave function in the k direction changes with time, but the change in time is proportional to the time derivative of the Hamiltonian. So this tells you that when the time variation is slow, then the system stays to lowest order in this instantaneous eigenstate. This is a more concrete way of saying that when the time variation of parameters in the Hamiltonian is very slow, and if I prepare the system in some eigenstate, it's some energy state, the system tries to stay in that state. It doesn't get very excited. So that means slow variations do not lead to excitations. By excitations, I mean that the AKs for k not equal to n become appreciable. This is physically quite intuitive. Every physical system has a time scale associated with it. And if the change of the system in time is very slow, the system gets a lot of time to adjust to that state. This simple intuitive result is actually a theorem in quantum mechanics. It's called the Adiabatic theorem. The Adiabatic theorem ensures that a slowly varying Hamiltonian stays in its initially prepared state to the lowest order. So in our quantum quench problem, what this means is that if I have a coupling which changes like this, and if I prepare the state of the system such that it is in a ground state at very early times, and if the change of the system is very slow, then it prefers to stay in the ground state. That, of course, is a lowest order effect. The corrections to this statement, which are the excitations, are controlled by some dimensionless number. And for what is the dimensionless number? You can see that in those expressions, there is difference of energy levels which appear everywhere. And you can see that if the difference of energy levels is large, then the left-hand side is small. If the difference is small, the left-hand side is large. The left-hand side being large means that the system is getting excited. So it must be that the spacing of the energy levels at a given time controls how good the adiabatic theorem is. So, or corrections to adiabatic evolutions. When the initial state is a ground state, which I'll call 0, then in that expression of difference of energy levels, what will appear is the gap in the spectrum. This is the energy gap in the spectrum. At time t. Then the result is that this adiabatic evolution is good when the time derivative of this energy divided by the energy gap square, the magnitude of this is much, much smaller than 1. You can see that such an object must appear in this discussion. Energy has dimensions of 1 upon the time. So the derivative of energy with respect to that time has dimensions of 1 upon time square. And so this quantity is dimensionless. And of course, when we say some quantity is large or small, it has to be a dimensionless quantity. And this is the right dimensionless quantity, which follows if I carry on the analysis which I got started on. So now we are done with most of the math. And I will now proceed to just do some very simple dimensional arguments to obtain something very interesting. Let us suppose that the parameter which is changing in time, which I've called g of t, has a form say something like this. Starts with g0, ends with g1. Whether g is positive or negative doesn't really matter. The important thing is that it crosses the critical point, which is g equal to 0, at some time which I've chosen to be t. The way I have drawn it, it is clear that at early times, this function g of t is varying very slowly with respect to time. Therefore, it must be true that at least in this region, I have adiabatic evolution. What does this mean? If I start with the system in its ground state, it basically stays in the ground state. The only thing that happens is that the wave function acquires a phase, which is quite typical. However, at later times, as g of t approaches 0, the energy gap, Eg at 0, is in fact exactly 0. So as I approach this point, the energy gaps keep decreasing. If the energy gaps keep decreasing, this left-hand side object keeps increasing, and very soon it's going to become bigger than 1. Adiabatic evolution will fail. Physically, it is obvious why this thing happens. As the energy levels, the energy spacings change in time, and if they keep decreasing, it becomes much easier for the system to get excited to the next excited state. However, there are very few theoretical tools to analyze a problem which is like this beyond perturbation theory when the adiabatic expansion fails. So here it becomes non-adiabatic and it is difficult to resolve. And it stays that way till once again the change of the coupling becomes slow and adiabatic evolution, in fact, resumes. So it is in this intermediate region system gets excited. And things start happening. In such a situation, let me draw this diagram again. I've drawn a very simple time dependence. It doesn't need to be that simple. I mean, so long as it is smooth. There is a time where the adiabatic evolution breaks down. This time it's called a Kibble-Zurek time. Let us now try to estimate the Kibble-Zurek time. The Kibble-Zurek time is defined the time, it's called TKZ, which has where this adiabatic parameter, namely the time derivative divided by the gap square itself, in fact just becomes 1. So if I know the time dependence of Eg of t, if I know that function, I can calculate what t equal to what t kz is. If you look at this picture and look near the critical point, so near the critical point, the coupling generically goes linearly in time. You can see that in this picture, this is basically a straight line which looks like this. This is again the generic situation. You can fine tune and have Quench protocols where it is like quadratic or cubic, and there is a similar analysis for this. The parameter V is the Quench rate. This is the rate at which the coupling changes as a function of time. Now, this relationship is of course true only near the critical point. Clearly, very far away from the critical point, there is a non-trivial function g of t. Good. Now, we argued that the energy gap near a critical point, near an equilibrium critical point, goes as this parameter, the magnitude of this parameter raised to the power z times nu. Okay. Now, for t less than tz kz, adiabatic evolution is valid. What does that mean? Is that the instantaneous gap is nothing but g of t raised to the power z nu. If I use this equation, this is vt raised to the power z nu. Okay. So if Eg of t is Vt raised to the power z nu, dEg dt, I'm ignoring coefficients, which is not the point here, is of course v to the z nu, t to the z nu minus 1 upon Eg square dg dt becomes v to the z nu, t to the z nu minus 1, v to the minus 2 z nu, and t to the minus 2 z nu. So this is v to the minus z nu, t to the minus z nu plus 1. And therefore, this tells you that the Kibble-Zurek time happens when equal to 1. But all these equal signs you should really think of the order of 1. That tells you that the Kibble-Zurek time goes as v to the z nu by z nu plus 1. With the minus sign, I guess. You can now substitute the Kibble-Zurek time into the energy expression for the energy at this time. You can calculate. And the result is the energy gap. This is the energy gap. TKZ is V to the Z nu by Z nu plus 1, because you just have to do a simple calculation by using, this kind of fact. So this tells you that the energy gap, the instantaneous energy gap at the Kibble-Zurek time. What do you do after that? As I said, after the Kibble-Zurek time, adiabatic evolution has broken down. So this is TKZ. This is the region of excitations. In 1970s, Tom Kibble, who is the pioneer who looked into this problem, made two very drastic assumptions. The first assumption he made was for T greater than TKZ, the system gets frozen. That means another word of saying is instead of adiabatic, it becomes diabatic. What does that mean? That physical quantities between this time TKZ and some later time T0 in this particular region do not appreciably change as a function of time. Physically, what this means is as follows. At the Kibble-Zurek time, it's like the threshold of the validity of adiabatic expansion. Once the adiabatic expansion has stopped, the system just gets excited. And of course, the system is going to get excited very slowly. But what Kibble assumed is to say, well, let's assume that the system very quickly gets into the mode that excitations start happening like mad. If the excitations start happening like mad, the system really doesn't get, and so basically, so far as the intrinsic time scales of the system are concerned, the parameters are just changing too fast. If the parameters are changing too fast, the system just cannot cope up with it. So the system just says, well, everything is changing so fast, so I just stay put. This is exactly what happens when in the kind of examples which are described in my first lecture, where the coupling goes suddenly from one value to another value. At this time t equal to 0, the state of the system doesn't change. The state at a time which is a little bit earlier than this point is almost exactly the same as the state which is a little bit later. What Kibble assumed is that even though there is a smooth evolution, such a thing in fact happens. The second thing which Kibble assumed is that the basic intuition of critical phenomena, namely that there is a single length scale in the problem and everything else can be determined by dimensional analysis, continues to hold that the correlation length is the only scale in the problem. What that means is, in this critical, this is called the critical region, we can calculate anything by the glorified dimensional analysis typical of critical phenomena. And one of the interesting objects, so for example, if there is an operator which has dimension delta, what this means is that this should go as Kibble-Zurek raised to the power minus delta. And what is xi? Recall that the energy gap is xi raised to the power minus z, where z is this dynamical critical exponent. So if I know what the energy gap is as a function of the speed of quench, just like this, I know how basically, so what this means is, in fact, let me write down. Just this factor of z taken out and a negative sign. Very good. The kind of phase transitions I talked about in a magnet is an example of an order-disorder transition. So magnetism is an example of an order-disorder transition. Why is it called an order-disorder transition? Because for t less than Tc, if I take the sample, it has the property that these little dipoles which make up the magnet try to align with each other. Whereas for t greater than Tc, they are randomly distributed, they randomly align. The magnetization is not equal to 0 in this phase, the magnetization is 0 in that phase. However, as I approach the critical point, the entire sample is not ordered in the same direction. So if the spins can be other than up and down, it can be aligned in different directions. In reality, domains are formed. These are called magnetic domains in a usual ferromagnet. What this means is that as you approach t, so if you suppose I start going from t greater than Tc towards the critical point t equal to Tc and beyond for t less than Tc, you are slowly cooling down a ferromagnet from the phase where all these dipoles were randomly aligned. So what happens is that the system starts looking as if broken up into little domains. Within each such domain, all the dipoles are aligned in the same direction. However, in neighboring domain, they can be aligned in a different direction. This is why they are called domains. And in reality, what happens as you cool down further, these domains start merging, and eventually almost the entire sample gets aligned. At the interface of these domains, what we have are what are called defects. How large can the domains be? Near the critical point, I said there is only one length scale in the problem. So it is natural to conjecture that the size of a domain should be order of the correlation length. So what this means is that the number density of domains the number density of defects should be the correlation, typically the correlation length raised to the power minus d, where d is the space dimension. Now, according to the Kibble-Zurek assumption, as the system is passing through the critical point, this is the frozen state. It is in this frozen state, as it is approaching this point, the domains start forming, the defects start forming. So there is a certain number of defects in this. The defect density, I'm sorry, this is not the number density, yeah. So the defect density which goes as xi to the minus d, but we know how xi behaves in this region because we assume that the system is frozen. So that scales as the speed of the quench raised to the power d nu by nu z plus 1. This formula is in fact quite remarkable. I tried to explain that the critical behavior is universal. The accurate statement is that the critical exponents are universal. What this really means that independent of the microscopic theory, there are many, many different kinds of systems which share the same values of the critical exponent. So in particular, nu is a critical exponent which is universal. The way the correlation length diverges as you approach the critical point is in fact very similar in many, many different kinds of systems. So what we have therefore achieved is in a non-equilibrium situation, it's clearly a non-equilibrium situation because things are getting excited, is that there is a universal prediction And the nice thing about universality is that since it does not depend on the details of the microscopic, you can use models to calculate universal behavior. For example, a very commonly used model for magnetism is the Ising model or the Heisenberg model. These are models. They do not accurately describe a real magnet for if I keep measuring all possible quantities. What they do, however, is to accurately predict for you the critical behavior of these of near the critical point. So in this context, what this means is that regardless of the details of the critical Hamiltonian, we have arrived at a result which depends only on universal quantities nu and z. This is called Kibble-Zurek scaling. And you must have felt very uncomfortable about the assumption which was made in deriving this, namely that the system makes a transition from adiabatic to diabatic transition suddenly. This, of course, in reality does not happen. However, it turns out that there are solvable models. Since it's a universal result, as I said, if it is universal, you can use a model to understand this. There are solvable models where this Kibble-Zurek scaling holds. And there are recent experiments, in fact. Also show some evidence. I must say that there is no general theoretical understanding of why this kind of rather striking result should actually hold. People understand it by model or in some experiments, but there is no general theoretical framework. It turns out, and this I will not go into at all, that in recent years, people have realized that many body systems can be mapped into theories that quantum many body systems some class of quantum many body systems can be mapped in fact to higher dimensional systems in classical general relativity. This is called gauge gravity duality. The most important example is called an ADS-CFT correspondence. It turns out that this process of quantum quench has an analog in general relativity in these higher dimensions. And since it is a classical general relativity, it's sort of easier to solve the problem, easier to understand how to deal with that problem. And in the context of those, we have in fact obtained some limited understanding of the origin of Kibble-Zurek scaling. And this is some work which I have done with Paula Basu quite some time ago. Finally, I should mention this is not the only universal result which you can obtain in critical quantum quench. See, one of the assumptions in the kind of quench scenarios which I did was that the initial, let me go back to this point. that the initial time evolution was slow. So there was an adiabatic evolution. Some time ago, in collaboration with and Robert Myers, we realized that we can study the problem in a general relativistic quantum field theory, where the initial rate of change is in fact very fast. And when the change is very fast, what we actually found is that there is a different kind of scaling behavior, which is also universal. The physics of that is very different from the Keeble-Zurek scaling, and I'll not go into that. I just wanted to give you an impression that this is an area of physics which has multiple applications to many different branches, as I sort of motivated in my very first lecture. And the interesting thing about this is that it uncovers universal physics. Now, in physics, anything which has universal result is interesting because it is independent of microscopic details of the system. And that is what happens in a rather non-trivial fashion for these examples of non-equilibrium physics. I think I'm going to end my lecture. I probably took a lot of time, but thank you very much for your patience. If you have any questions, I'm happy to answer.
Yeah, so any question? Yeah. Is there a mic or?
No, it's not working, so you should go there.
Yeah, it's better if you come close to somewhere I can hear properly.
And where is the mic? Here. Yeah, go near the mic.
So near a critical point, the system has continuous energy spectrum until it changes phase. So a system near a critical point,
Yes.
does it have a continuous energy spectrum near a phase near a critical point?
Very good question. Not necessarily. It can have a discrete spectrum, but the spectrum basically, I mean, there can be a band-like spectrum. Like there are lots and lots of states near the ground state, but there can be a gap above that. Above that band.
Okay.
The only thing that we require for this is that the gap itself is very small. In fact, vanishes at the critical point.
Okay. So a system. So what about the non-adiabatic evolution? Is a system that goes on non-adiabatic evolution? Does it have phase transitions?
Well, phase transitions is a slightly different question from time evolution. Phase transitions is a kind of can happen regardless of any kind of time evolution. So a phase transition typically happens for these kinds of phase transitions, which are critical phase transition, which, as you just said, when the gap vanishes. Now, when a system is evolving adiabatically, it can only do so if the gap is non-vanishing. Otherwise, the system will get excited. So basically, the system has to be far from a critical point. A phase transition is a critical point, is a point which marks the interface between phases, right? So of course, at any side of the critical point, it's in some phase. Now can ask that whether in that phase itself, you can have adiabatic evolution. If the phase is such that there is a non-trivial gap and the change of parameters of the system is slow compared to the gap, you can have an adiabatic evolution. There are examples where there is an entire phase which is gapless, and then there cannot be any adiabatic evolution.
So a system undergoes non-adiabatic evolution, does not undergo phase transition, right?
It is undergoing a phase transition. If
Okay.
it is non-adiabatic evolution, means that the system is excited. See,
Okay. Yeah.
Okay. Yeah.
Okay. So a system near an or a system in an intermediate state, does this system considered as a classical system?
For these quantum phase transitions, typically the interactions they're strongly coupled and they are very quantum and cannot be considered to be classical.
Mm-hmm.
However, there are analogs of this for thermal phase transitions, right? Where instead of talking of energy gaps, you just consider correlation functions. And it for these thermal transitions where Kibble first did the analysis, in that case, they are basically classical. When the temperature is finite, you don't have to take into account quantum effects. By quantum effects, I mean H bar effects.
Okay. So is there a reason why the critical behavior is universal?
Yeah, I tried to give a hint of that, why it is universal. It has got to do with the fact that at the critical point, there is scale invariance. As I sort of in my second lecture, it's very hard to explain in one single lecture. But the main point about a critical point is that the correlations are long range. Long range correlations mean power laws. Power law means that there is scale invariance. Okay. So what scale invariance means is that the system looks similar at different scales, right? Now, what does that mean? And this was the great insight of Kadanoff and Wilson is the following. So what they said, well, if the system is scale invariant, what I can do, I can, take the system and break it up into little blocks. And I can take these blocks, break them on into further blocks. So I typically start increasing the scale of the system, and the system should look similar, right? Now, how do I get from, so the picture, this was Kadanoff's picture. So you start, for example, with a set of spins like this. And what Kadanoff said, it sort of aligned them. So what I do, all of them need not be aligned. I mean, let me put a little things which are a little bit different. Let me take this, break it up into blocks. And now I get a new system where at every point of this block, for example, I take the average spin. I'm just drawing like this, okay? Now, the basic length scale is now bigger. And you keep doing it. You keep doing it till the size of the block is equal to the correlation length. Now, what are you doing in the process? You're basically averaging over the microscopic ingredients. And usually, when you average over microscopic ingredients, the details of the microscopic physics get washed away. It is the same reason as if you take a liquid which is made out of molecules, and if you make measurements at the scale of 1 centimeter, right? It doesn't matter whether the liquid is water or mercury or alcohol or what have you, right? It obeys the same kinds of equations.
Right.
So near the critical point, since there is scale invariance and the system looks very similar at different length scales, it must be that many different systems with many different microscopics have a similar behavior. So this is the main reason why there is universality near a critical point. Does it make
Yes.
sense?
Yeah. Yeah, thank you.
Thank you.
Any other question? Sumit, I have a quick question, and maybe we can chat later on Zoom.
Surely.
About the Kibble Zurich time. So you said that in the work you have done with Robert Myers, that you have found some critical behavior or something which is different from Kibble Zurich, right?
Right. So Kibble Zurich is valid when the initial time evolution is slow. Right. So, yeah, you always start with a system with an initial mass gap. And if the time evolution is slow at the scale of the mass gap, then there is a period of adiabatic evolution.
I see.
Okay. Now, what we considered is the opposite limit. The limit where the initial time evolution itself is fast compared to the mass gap. Okay. There is no adiabatic evolution in this, in that particular case.
No adiabatic region.
There's no adiabatic region, right? So the story is completely different. But we prove that in any relativistic theory, nevertheless, there are scalings of expectation values. By scaling means power laws, in power laws of this speed of the quench. And they are different power laws, but nevertheless universal.
Thank you.
So usually, and so what happens if you take a system and and this is something we did, for example, for the the transverse field Ising model. What you and you look at the system for various quench rates. And what you find when the quench rate is extremely fast at the scale of the lattice spacing, you get results which are like the sudden quench, which I described in the first lecture. And then you comes a phase when the quench rate is fast compared to the physical scales, but slow compared to the lattice scale. Then you get the scaling which I and Robert and Damien found. Okay. And finally, you get into a phase where the quench rate is slow compared to the physical scales, and then you get Kibble Zurich scaling. So there is a crossover of the scaling behavior.
Any other question before we go to the other speaker? All right. Well, thanks a lot, Sumit, for 3
Thank
lectures.
you very much.
It was great.
Okay. Thank you.
By the way, I think the stuff could be of interest in non-standard